Okay. Okay, guys. Sorry for the delay. Okay, so we just want to talk about ideals and some of the constructions you can do with them. So just like we have cosets of subgroups in group theory, we have cosets of ideals in ring theory. What is a coset? So let's take an ideal. Well, I won't call it a left coset. A coset of I is just defined to be like a coset of I like that. Okay, so take all the elements of the ideal and add x to everything. Okay. And then R mod I is the set of all the cosets. Okay. Okay. So we can take the set of cosets of an ideal and we can make up a new ring. And R mod I, the set of all the cosets, can be turned into a ring. By putting, we can add two cosets. You can make that the addition of cosets by just adding the two elements x plus y, then looking at that coset. We also need to define multiplication in R mod I, and we just multiply the two things. Take that left coset. You know, and I believe in Math 2272, you would have proved that if I is an ideal and R mod I, the operations on R mod I are well defined. And the proof of this just uses like the basic properties of that define an ideal. You know, for example, let's do this exercise. Like, let's suppose x plus y, this coset of x and x prime are equal, and the coset of y and y prime are equal. And let's show okay, let's show that the coset of xy is the same as the coset of x prime y prime. In other words, this says that if we take two different representatives of a coset, of each coset, then even though we took two different representatives, the resulting product is the same coset. So this would mean that multiplication of cosets is well defined. Okay, first of all, saying that x and x prime are in the same coset means that x minus x prime is in the ideal. So you know that x minus x prime is in the ideal. Similarly, we know that y minus y prime is in the ideal. What we want to show is that xy minus x prime y prime is in the ideal. That's our goal. Well, since we have two things in the ideal, let's see. What should we do? Xy minus x prime y prime. Well, we can rewrite it. We can rewrite it by adding 0. We can look at xy minus xy prime plus xy prime. Okay. Now, xy minus xy prime, that's just x times y minus y prime. And xy prime minus x prime y prime, that is x minus x prime times y prime. Now, this is an element of the ideal, and this is an element of the ring. This is an element of the ideal, this is an element of the ring. Okay, so the ideal is closed under multiplication by arbitrary elements of the ring. So x times this element of the ideal is still in the ideal. So this is in the ideal, this is in the ideal times this element of the ring. So this whole thing is in the ideal. Now we have an element of the ideal plus an element of the ideal. So this whole entire thing is in the ideal. Okay. In other words, xy minus x prime y prime is in the ideal. Okay. And that means that xy and x prime y prime define the same coset. And that means that we can define multiplication of cosets. And just to illustrate what is really happening, you know, look at things, we could look at the integers mod 6. We know that 2 is the same as 8 mod 6. And we know that 3 is the same as -9 in z mod 6z. And the result of this calculation would tell us that 2 times 3 is the same as 8 times, well, I don't want to use 2 and 3. Sorry, let me say 1 and -11, and let me say 4 and 16, for example. Okay, now what should happen is that 1 times 4 should be the same mod 6 as -11 times 16. Okay, we work it out, we get 4 on the left-hand side. And -11 times 16, well, you know, so you get -176. Well, negative 180 is divisible by 6, so this is negative 180 plus 4. In other words, it's a multiple of 6 plus 4. So the coset of 4 and negative 176 are equal, as we wanted. So 4 bar equals negative 176 bar, which kind of like reassures us, I guess. Okay, so these this definition for the ideal ensures that we can turn the set of cosets into a ring. Okay. Now, we know that there is a relationship between normal subgroups and homomorphisms. Well, there's also a relationship between ideals and group homomorphisms, or sorry, ring homomorphisms. Sorry. Okay, so let's first define what a ring homomorphism is. Well, if you can guess, it is something that preserves addition and multiplication, and we also require another restriction for it. So let's take two rings. Let phi from R to S just be some function. And phi is called the homomorphism. If phi of R plus R prime should be phi of R plus phi of R prime for all R and R prime and R. 2. Phi of R prime should just be phi of R times phi of R prime. Again, for all R and R prime. 3. Phi of, I'll write 1 sub R for the multiplicative identity of R. That has to be the multiplicative identity of S. Notice this is kind of a departure from the definition for groups. Like in group theory, we just have one condition for addition, like for the group operation. And we get, when we're talking about groups, phi of the identity of the group is equal to the identity. That comes automatically. But for ring homomorphisms, we have to impose this extra condition. Okay. Okay. And then, then the last thing I want to talk about today is the relationship between ideals and ring homomorphism. Okay, first of all, whenever we have an ideal, we get a ring homomorphism. So proposition, let R be a ring, and I an ideal. And let's define phi from R to R mod I by, well, we map X, an element to the ring, to the coset of X. Okay. Then phi is a homomorphism. Not only that, phi is onto, and phi of X equals phi of Y, if and only if X minus Y is in the ideal. Okay, so what this tells you is that if you have an ideal, you get a homomorphism. Okay. So if you start with an ideal, you get a homomorphism. Let's check that we get a homomorphism. And I'll just leave these two properties. You can check them if you want. Let xy be an I, and phi of X plus Y, that's just the coset of X plus Y, and the definition of addition in the cosets says that you just add the coset of X plus the coset of Y. And again, this is just phi of X plus phi of Y. Okay, what about phi of XY? Well, it's just XY, coset of XY, and then we saw that that's just a coset of X times a coset of Y. That's just phi of X times phi of Y. And then what is phi of 1? Well, that's just the coset of 1. I'll put a 1 so it's more clear that it's a 1. And just now is just to verify that the coset of 1 is the identity, the multiplicative identity of R mod I. So if you check that, like 1 plus I times X plus I, that's just 1x plus I, that's just X plus I. Okay, that shows that coset of 1 times any coset equals that same coset. So 1 plus I, the coset of 1, that's the multiplicative identity. Okay, so this tells us that phi of 1 is the identity of R mod I. So phi is a homomorphism. Oh yes, so I did say let xy be in I. That makes no sense. Sorry, you are correct. It should be xy in R. Sorry about that. Because what we're checking is that we're checking 5x plus y equals 5x plus phi of y, 5xy equals 5x phi of y, and phi of 1 equals 1. And we have checked all those things, so we have a homomorphism. Okay. So now we can take an ideal and get a homomorphism. Now let's try and do the reverse. Let's take a homomorphism and get an ideal. Okay. And if you remember, group theory is the same idea. Let's take a homomorphism. And then define the kernel of phi. This is going to be all the elements of R such that phi of R equals 0. Then, oh yeah, so, okay, that is the definition of the kernel of phi, our proposition, is that the kernel of phi is an ideal, excuse me, of R. Not only that, kernel of phi is 0 if and only if phi is 1 to 1. So the kernel is kind of a detector for when phi is a 1-to-1 function. Okay. And let's see why that is. Why is kernel of phi an ideal? Well, we just asked, what is phi of yx? Well, that's just phi of y times phi of x, since phi is the homomorphism. Well, that's just phi of y times the 0. Everything in the kernel, so the definition of kernel says that phi of x should be 0, so it's just phi of y times 0. Now, anything times 0 is just 0. That tells you that yx is in the kernel whenever x is. Okay. So that tells you that the kernel is closed under multiplication by elements of the ring. And then you would also have to check that phi of 0 equals 0, and check that if x and x prime are in the kernel of phi, then phi of x phi of x minus x prime equals 0, meaning that x minus x prime is in the kernel. Okay, so you check those two things, then that tells you that kernel of phi is an ideal, along with this first part. Okay, so now every homomorphism gives us an ideal. Every ideal gives us a homomorphism. But not only that, there's like a way, there's kind of like an equivalence between the two. That's the first isomorphism theorem. That is, we'll probably start next class with just the definition, like just the isomorphism theorems. Okay, so let me just stop here. If you want, I guess it will just be a weekly thing, but completely optional and also anonymous. So you only have to fill it out if you want to. And just so you know, there's no way that I can tell who filled it out. Yep. So yeah, let's just stop there. The reason I'm stopping 5 minutes early, I guess, is theoretically you now have 5 minutes to fill out the form if you want. Okay, so that is pretty much it. Just finally, let me just remind you, exam on April 7th, assignment 6 due on Monday. Okay, that's it for me. So see you guys on Monday.